Good day, students. In this session, we're going to discuss determining whether an equation is an identity or a conditional equation. So, the core idea, an equation is an identity if its solution set is the same as the domain of the variable. Otherwise, it is a conditional equation. So, for the learning outcomes, determine whether an equation is an identity or a conditional equation. Recall that an equation in terms of a variable x is a statement that two expressions in terms of x is equal. Here are some examples of algebraic equation. X minus 1 equals 0, x squared equals 4, x plus 3 equals 3 plus x minus 2 all over x minus 2 equals 1. The domain of a variable in an equation is the set of numbers for which the algebraic expression in the equation are defined. In the equation shown, the domain of the variable x is the set of real numbers. X minus 1 equals 0, x plus 3 equals 3 plus x squared equals 4. The value of x is a real number. In the equation, x minus 2 all over x minus 2 equals 1, the expression in the left side is not defined when x is 2. Thus, the domain of the variable x is any real number except positive 2. Also, recall that the solution of an equation is a number that satisfies the equation. It is a number that when replaced to the variable, the resulting statement will be true. Moreover, the set of all solutions to the equation is called the solution set of the equation. Here are some examples. In the equation x minus 1 equals 0, if x is replaced by 1, the resulting statement is true. But if x is replaced by a number other than 1, the resulting statement is false. Thus, the only solution to the equation is 1, and the solution set is positive 1. In the equation x squared equals 4, if x is replaced by either negative 2 or 2, the resulting statement is true. And if x is replaced by any number other than negative 2 or 2, the resulting statement is false. Thus, the solutions to the equation are negative 2 and 2, and the solution set is negative 2 and positive 2. In the equation x plus 3 equals 3 plus x, if x is replaced by any real number, the resulting statement is true. Thus, the solution set is the set of real numbers. In the equation x minus 2 all over x minus 2 equals 1, if x is replaced by any real number except 2, the resulting statement is true. Therefore, the solution set is the set of the real number except 2. With the knowledge we learned about the domain and the solution set of an equation, we can now define the identity and conditional equation. An identity is an equation in one variable such that the solution set of that equation is the same as the domain of the variable. A conditional equation is an equation such that there is at least one number in the domain of the variable that is not in the solution set. For example, identify the domain and the solution set of the following equations and determine if it is an identity or conditional equation. So we have x minus 1 equals 0, x squared equals 4, x plus 3 equals 3 plus x, and x minus 2 all over x minus 2 equals 1. We identify the domain and the solution set of the equation and conclude if it is conditional or identity. Since there is at least one number in the domain that is not in the solution set of x minus 1 equals 0, it is a conditional equation. Since there is at least one number in the domain that is not the solution set of x squared equals 4, therefore it is a conditional equation. For these equations, they are identities because the domain and the solution set are the same. So for x plus 3 equals 3 plus x, the domain and the solution set are both set of real numbers. For the equation x minus 2 all over x minus 2 equals 1, the domain and the solution set are both x such that x is set of real number except positive 2. In summary, an identity is an equation in one variable such that the solution set of that equation is the same as the domain of the variable, while a conditional equation is an equation such that there is at least one number in the domain of the variable that is not the solution set. Here are the references used in this learning module. Now, let's proceed to deriving the fundamental trigonometric identities. In applying appropriate trigonometric identities in solving situational problems, you should derive the fundamental trigonometric identities. The fundamental trigonometric identities can be derived by applying the basic operations on trigonometric identities and applying the Pythagorean theorem. For the learning outcome, it is expected for you to derive the fundamental trigonometric identities. Let us start today's lesson from drawing an angle, theta, in the Cartesian coordinate plane as shown in the figure. A point P, xy is plotted in the terminal side of the angle theta. Let x be the distance of the point P from the y-axis or abscissa, y be the distance of point P from the x-axis or ordinate, and r be the distance of point P from the origin. We can get the value of r from x and y using the distance formula. R equals square root of x squared plus y squared. For a particular angle theta, there are 6 ratios that can be formed from x, y, and r that can be described the angle theta. These ratios are sine, cosine, tangent, cotangent, secant, and cosecant. If theta is an angle in standard position, point P in terms of xy is any point except the origin on the terminal side of theta, and r is a distance of the point P from the origin such that r equals square root of x squared and y squared, then sine theta equals y over r, cosine theta equals x over r, tangent theta equals y over x. If x is not equal to 0, then cosecant theta equals y over r if y is not equal to 0, secant theta equals r over x if x is not equals to 0 or not equal to 0, and cotangent theta is x over y if y is not equal to 0. Let us have an example. Find the values of 6 trigonometric functions of angle theta in standard position. So the point is 3, 4 on the terminal side of theta. Figure shows an angle theta with the point 3, 4 on its terminal side. Using the distance formula, r equals 5. Since x equals 3, y equals 4, and r equals 5, from the definition, we can get the 6 trigonometric functions. Sin theta is equal to 4 over 5, cosine theta is equal to 3 over 5, tangent theta is equal to 4 over 3, cosecant theta is equal to 5 over 4, secant theta is equal to 5 over 3, and cotangent theta is equal to 3 over 4. It can be observed from the definition that when the functions are defined, cosecant theta and secant theta are reciprocals of sine theta and cosine theta respectively. From the definition, sine theta equals y over r. If we can get the reciprocal of both sides, we have 1 over sine theta equals r over y. Since r over y is equal to cosecant theta, we have cosecant theta equals 1 over sine theta. We can also use the same method for cosine theta. From the definition, cosine theta equals x over r. If we get the reciprocal of both sides, 1 over cosine theta equals r over x. Since r over x is equal to secant theta, we have secant theta equals 1 over cosine theta. Also, it can be observed from the definition that when the functions are defined, cotangent theta is the reciprocal of tangent theta. From the definition, tangent theta equals y over x. If we get the reciprocal of both sides, we get 1 over tangent theta equals x over y. Since x over y equals cotangent theta, we have cotangent theta equals 1 over tangent theta. The equations cosecant theta equals 1 over sine theta, secant theta equals 1 over cosine theta, cotangent theta equals 1 over tangent theta are true for all values of theta which each side is defined, and they are called reciprocal identities. We can also obtain, based from the definition, that the quotient of sine theta and cosine theta is tangent theta, and the quotient of cosine theta and sine theta is cotangent theta. The illustration shows that sine theta over cosine theta is equal to tangent, and cosine theta equals sine theta is equal to cotangent theta. The equations tangent theta equals sine theta over cosine theta and cotangent theta equals cosine theta over sine theta are true for all values of theta for which each side is defined, and they are called quotient identities. We can also derive the relationship of sine theta, cosine theta in the distance formula. From the figure, y squared plus x squared equals r squared. Since r is not equal to 0, we can divide both sides by r squared, and we have y squared over r squared plus x squared over x squared equals 1. Since sine theta equals y over r and cosine theta equals x over r, we can have sine squared theta plus cosine squared theta equals 1. The equation sine squared theta plus cosine squared theta equals 1 is called the fundamental Pythagorean identity because it was obtained from the distance formula, which was obtained from Pythagorean theorem. We can also derive the other Pythagorean identity from the fundamental Pythagorean identity. Sine squared plus cosine squared theta equals 1. If cosine theta is not equal to 0 and we divide both sides of cosine squared theta, we get tangent squared theta plus 1 equals secant squared theta. On the other hand, if sine theta is not equal to 0 and we divide both sides by sine squared theta, we get 1 plus cotangent squared equals cosecant squared theta. The equations tangent squared theta plus 1 equals secant squared theta and 1 plus cos tangent squared theta equals cosecant squared theta are valid when these are defined, and they are called Pythagorean identities. Now, let us derive the even-odd identity by drawing positive angle and negative angle theta on the same plane as shown in the figure. A point P in terms of xy is plotted in the terminal side of the angle theta, and another P prime, x prime, y prime is plotted in the terminal side of negative angle theta. The sine and cosine values of negative theta are sine of negative theta equals y prime over r prime, and cosine of negative theta equals x prime over r prime. Also, from the figure, x prime is equal to xy prime is equal to negative y, and r prime is equal to r. Here is a derivation of 6 trigonometric functions of negative angle in terms of its positive equivalent. In addition, the 8 fundamental identities, the shown identities are valid when they are defined, and they are called even-odd trigonometric identities. In summary, the relationships given by the reciprocal, quotient, and Pythagorean identities constitute the 8 fundamental trigonometric identities. Here are the references used in this learning module. Always remember, do mathematics to learn mathematics. Practice, improve, and stay curious. Keep safe, stay healthy, and God bless everyone. See you next time in our next lesson.